Have you ever looked up at the night sky and felt that profound, humbling sense of wonder? That feeling is just the beginning, because what lies beyond our atmosphere is so much larger and stranger than most of us can possibly conceive. Out there, drifting in the vast ocean of space, are billions of galaxies, each one an island of stars, planets, and mysteries we're only just beginning to understand. And while we might recognize a few of their names or shapes, the true nature of these cosmic giants remains one of the universe's best-kept secrets until now. Today, we're setting off on a journey far beyond our solar system, beyond the Milky Way, and into the heart of galactic phenomena that defy logic and stretch our imaginations to their absolute limits. We'll explore 30 mind-bending facts about galaxies that aren't just surprising, they're paradigm-shifting. These are the kinds of revelations that don't just add to what you know, they completely reshape how you see reality itself. From galaxies that shouldn't exist according to our current laws of physics, to black holes with appetites so enormous they consume entire star systems, what we're about to uncover will challenge everything you thought was true about the cosmos. This isn't just a list of trivia, it's an invitation to reimagine the universe. Each fact is a thread in a much larger tapestry, a story written in starlight and mystery, waiting for curious minds like yours to unravel it. So get comfortable, open your mind, and let's dive deep into the extraordinary. By the time we're done, you won't just see the night sky differently, you'll understand just how astonishing, how beautiful, and how wonderfully strange our universe truly is. Let's begin with a fact that hits close to home because it's about our own cosmic address. We call it the Milky Way, a name that sounds almost gentle and familiar. But the reality of our galaxy is anything but small or simple. To start to grasp its size, picture this. From one glittering edge to the other, the Milky Way spans about 100,000 light-years. Now, a light-year isn't a measure of time. It's a measure of distance, the staggering distance a beam of light travels in one entire year. And since light moves at over 1 billion kilometers per hour, that single year-long journey covers an almost inconceivable 9.5 trillion kilometers. Now, multiply that by 100,000. That is the diameter of our home galaxy. Within that vast expanse, our galaxy is home to an estimated 100 to 400 billion stars. Think about that number for a moment. If you tried to count every single star at a rate of 1 per second, it would take you thousands of years just to get through a fraction of them. Our sun, the powerful anchor of our entire solar system, is just one of those hundreds of billions of specks of light, and our solar system itself, it's located in a relatively quiet suburban spiral arm called the Orion Cygnus Arm, roughly 27,000 light-years from the chaotic and energy-packed galactic center. This is where the scale becomes truly insane. Even if you could build a spacecraft capable of traveling at the ultimate speed limit of the universe, the speed of light, a journey across the Milky Way would still take you 100,000 years. For context, 100,000 years ago, modern humans were just beginning to migrate out of Africa. The entire span of recorded human history from the first civilizations to today is only about 5,000 years. A crossing of our own galaxy would take 20 times longer than all of that. It's a humbling reminder that even with our most ambitious technology, we are, for now, permanent residents of this single, magnificent island of stars, a tiny but wondrous part of an almost unimaginably large cosmic structure. But if the sheer size of our galaxy makes you feel small, this next fact might just redefine your entire understanding of what a galaxy even is. We look up and see a beautiful, glittering collection of stars, but the incredible truth is that everything we can see, every single star, every nebula, every planet, is just the faint, glowing tip of a much larger, much darker iceberg. Astronomers estimate that roughly 85% of the matter in a galaxy like ours is completely invisible. This missing mass is known as dark matter, and it is arguably the single greatest unsolved mystery in all of modern physics. We call it dark not because it's black or shadowy, but because it doesn't interact with light in any way we can detect. It doesn't emit it, it doesn't absorb it, and it doesn't reflect it. It is utterly and completely transparent to the entire electromagnetic spectrum. So how on earth do we know it's there? The answer lies in gravity. We can observe its powerful gravitational effects on the things we can see. Think of it like watching leaves swirling in a gust of wind. You can't see the wind itself, but you can clearly see its influence on the leaves. The most compelling evidence for dark matter comes from watching how stars orbit the centers of their galaxies. According to the laws of gravity, stars on the outer edges of a spiral galaxy should move much more slowly than those closer to the dense center, similar to how Pluto orbits our Sun much more slowly than Earth does. But that's not what happens. Observations show that stars on the outskirts of galaxies orbit at nearly the same high speed as those near the middle. The only explanation is that each galaxy is embedded within an enormous, massive sphere of this invisible dark matter, a halo that extends far beyond the visible edge of the galaxy itself. Its immense gravitational pull is whipping those outer stars around, forcing them to move at velocities that should otherwise fling them off into intergalactic space. This means the beautiful spiral we see when we look at a photograph of the Andromeda galaxy is just the luminous core of a far more massive and entirely unseen structure. Without dark matter's gravitational scaffolding, galaxies as we know them simply wouldn't have been able to form in the early universe. It is the hidden architect of the cosmic web, the invisible backbone upon which the visible universe is built. We are left with a profound and humbling realization. Most of the universe is made of something we cannot see, cannot touch, and do not yet understand. And if the idea of an invisible cosmic scaffolding makes the universe feel strangely incomplete, just wait until you hear about the ultimate galactic destiny that awaits us. Everything in the cosmos is in motion, and our Milky Way is on an inescapable collision course with our nearest giant neighbor, the Andromeda Galaxy. Thanks to precise measurements from the Hubble Space Telescope, we know these two spiral giants are racing toward each other at an astonishing velocity of about 110 kilometers per second. That's a journey from Earth to the Moon in less than an hour. Now, the word collision probably brings to mind a violent, catastrophic event, a cosmic car crash of unimaginable proportions. But the reality is far stranger and much more beautiful. While the merger is indeed set to begin in about 4.5 billion years, the outcome won't be destruction. It will be a magnificent rebirth. The insane part of this whole story is that despite the sheer scale of these two galaxies, they are mostly empty space. The average distance between stars is so vast that it's highly unlikely any two stars will actually collide. Think of it like this: if you were to scale down the entire galaxy, making our Sun the size of a single grain of sand, the next closest star would be another grain of sand over 4 miles away. Now imagine two huge crowds of people, each several miles across, moving slowly toward each other. The crowds will eventually merge and mingle, but the chances of any two individuals actually bumping into each other are incredibly slim. That's exactly what will happen with the stars in the Milky Way and Andromeda. So what will happen? Over billions of years, the mutual gravitational pull of these two galaxies will completely distort their beautiful spiral shapes. They will swing past each other, their structures stretching and warping, creating long, streaming tidal tails of stars thrown out into the darkness. Eventually, after a few more close passes, they will settle down and completely merge, coalescing into a new, single, giant galaxy. Astronomers have already given this future colossal entity a nickname, Milkdromeda, or sometimes Milkomeda. This new galaxy will likely be a huge, blob-like elliptical galaxy, devoid of the distinct spiral arms we see today. the night sky from any surviving planets within it would be utterly transformed, blazing with the combined light of over 1 trillion stars. It's a humbling and peaceful thought. The most dramatic event in our galaxy's future won't be a firestorm of destruction, but a slow, graceful, and majestic dance, a cosmic merger that writes a new chapter in the story of the universe, with our solar system likely surviving as a silent witness to the spectacle. But while the long-term fate of our galaxy is a slow, majestic dance, its current heart beats to a much more intense and violent rhythm. Tucked away in the very center of the Milky Way, hidden behind thick clouds of interstellar dust and gas, lies a monster of almost unimaginable power, a supermassive black hole named Sagittarius, a star. This isn't just a dense object, it's a gravitational leviathan weighing in at a staggering 4.1 million times the mass of our Sun. And the truly mind-bending part is that Sagittarius, a star, is not unique. We now believe that at the center of nearly every large galaxy, there lurks a similar supermassive black hole, each one the dark, beating heart of its cosmic island. To even begin to grasp the scale of these entities, consider that the event horizon of our galaxy's central black hole, the point of no return where not even light can escape, is about 24 million kilometers across. That sounds vast, and it is, but it's also incredibly compact for an object of its immense mass. If you could replace our Sun with Sagittarius, a star, its event horizon would extend out past the orbit of Mercury. Its gravitational influence, however, reaches far, far beyond that invisible boundary, dictating the motions of stars thousands of light years away. For a long time, we thought of black holes as the universe's ultimate vacuum cleaners, silent, insatiable, and destructive. But the reality is so much more fascinating and complex. These supermassive black holes are more like active, regulatory engines for their galaxies. Their immense gravity doesn't just consume, it also creates. As vast clouds of gas and dust are pulled inward, they don't fall in directly. Instead, they form a superheated, spinning disk of material called an accretion disk, whirling around the black hole at nearly the speed of light. The friction within this disk heats it to millions of degrees, causing it to glow with the intensity of billions of stars and blast out enormous amounts of radiation across the universe. This energetic output is so powerful that it can literally blow away the raw materials for star formation, the gas and dust from the central regions of the galaxy. In this way, a supermassive black hole can act as a cosmic thermostat, switching off the birth of new stars and putting a limit on how large its host galaxy can grow. In their most extreme and active state, when they are consuming matter at a ferocious rate, we call them quasars. A quasar can outshine its entire host galaxy by a factor of 1,000, becoming the single brightest object in the entire cosmos, visible from billions of light years away. The relationship between a galaxy and its central black hole is a delicate and co-evolutionary dance. The galaxy feeds the black hole, and the black hole, in turn, feeds back energy that shapes the galaxy's future. It's a cycle of creation and destruction happening on an epic scale, proving that even in the darkest corners of space, there is a dynamic and powerful force guiding the evolution of the cosmic structures we see today. These black holes are not just occupants of their galaxies. In a very real sense, they are the defining core, the architects of their grandeur, and the ultimate arbiters of their destiny. And just as every galaxy seems to host a supermassive black hole, each one also boasts a unique and stunning physical form. When we picture a galaxy, most of us imagine a majestic spiral, much like our own Milky Way or its famous neighbor, Andromeda. For decades, astronomers classified these cosmic structures using the Hubble sequence, a sort of cosmic filing system that sorts galaxies into neat categories: spirals, ellipticals, and irregulars. But the deeper we look into the universe, the more we discover that this system is merely a starting point. The true diversity of galactic shapes is far wilder and more bizarre than anyone initially suspected. revealing a universe that loves to experiment with form on the grandest of scales. Beyond the classic pinwheels and smooth, fuzzy ellipses, there exist galactic oddities that look like they were dreamed up in a science fiction novel. Take ring galaxies, for instance. These incredible structures look exactly like their name implies, a perfect, luminous circle of stars against the black velvet of space, often with a bright knot of stars in the very center, creating a cosmic bullseye. The most famous example is Hoag's object, a galaxy so perfectly ring-shaped that when it was first discovered, astronomers thought it might be some kind of imaging trick. The prevailing theory for how these form is as violent as it is precise. Astronomers believe a smaller galaxy must have shot like a bullet directly through the center of a larger spiral disk galaxy. This head-on collision sent a powerful gravitational shockwave rippling outward through the victim galaxy, compressing gas and dust and triggering a massive wave of new star formation in a perfect, expanding ring. It's a celestial work of art born from a catastrophic event. Then there are the lenticular galaxies, a strange and often overlooked hybrid. They possess the central bulge of a spiral galaxy and a large, disk-like structure, but they are completely devoid of the beautiful, star-forming arms that define their spiral cousins. They look, for all intents and purposes, like a spiral galaxy that has somehow faded or been smoothed out. They represent a fascinating transitional phase, often thought to be aging spirals that have used up or lost most of their interstellar gas, leaving them without the material needed to create new stars and maintain their distinctive structure. They are the cosmic equivalents of a retired athlete still possessing the powerful build of their youth, but no longer actively engaged in the game. But perhaps the most ghostly and puzzling of all are the ultra-diffuse galaxies. Imagine an object the size of our entire Milky Way, which spans 100,000 light-years. Now, imagine that instead of containing hundreds of billions of stars, this galaxy holds only 1% of that number, just a few billion stars. The result is a vast, wispy, and almost transparent ghost of a galaxy. These faint giants are so sparse that if you were standing on a planet inside one, your night sky would be nearly empty, with stars few and far between, offering a hauntingly clear view into the blackness of intergalactic space. Their existence is a monumental challenge to our understanding of dark matter. A galaxy that large should be held together by an enormous, massive halo of dark matter. But some of these ultra-diffuse galaxies appear to have very little, if any, suggesting that either dark matter can be stripped away or that galaxies can form in ways we have not yet begun to comprehend. They are fragile cosmic enigmas, whispering secrets that could potentially rewrite the rules of galaxy formation. This brings us to one of the most profound and somber concepts in all of cosmology: galactic death. We tend to think of galaxies as eternal, unchanging tapestries of light, but just like living things, they have a life cycle. They are born, they evolve, and yes, they can die. Astronomers have a specific, chilling term for this process: quenching. It's the moment a galaxy's engine of creation sputters and stops, when it can no longer form new stars. The insane reality is that our universe is already littered with the corpses of these cosmic giants, galaxies that have become celestial zombies, still shining but devoid of any new life. To understand this, we have to rewind the cosmic clock. In the early universe, galaxies were frenetic, chaotic, and incredibly fertile places. They were bloated with vast, cool reservoirs of hydrogen gas, the raw material for star birth. Gravity would pull clumps of this gas together until they collapsed under their own weight, igniting the nuclear furnaces that create new stars. This period was a true cosmic renaissance, a brilliant firestorm of creation lighting up the darkness. But for many galaxies, that era of abundance didn't last. Something happened that either cut off the gas supply or made it impossible to use. The most obvious corpses in this cosmic graveyard are the giant elliptical galaxies. These are the red and dead galaxies. If you look at them through a powerful telescope, they appear as a soft, fuzzy glow, a smooth and featureless blob of light. Their distinct red color is the ultimate giveaway. Why red? Because the only stars left shining within them are old, cool, low-mass red stars. All the massive, hot, blue stars that burn bright and die young have long since exploded as supernova, and there was no new gas left to create replacements. Without any young, blue stars, the galaxy takes on a permanent crimson hue. It's a galaxy in retirement, its glory days of star formation billions of years behind it. But the truly mysterious cases aren't the ancient, red and dead galaxies, it's the ones that were quenched prematurely. These are galaxies that, by all accounts, should still be vibrant and blue, churning out new generations of stars. They have plenty of mass and should have access to gas, but somehow their fuel supply has been violently cut off. Astronomers are like cosmic detectives trying to solve this murder mystery, and they have two prime suspects. The first is an internal killer, the supermassive black hole at the galaxy's heart. As we discussed, when these monsters feed, they don't do so quietly. The incredible energy released from their accretion disks can blast outwards in the form of powerful jets and radiation. This outburst can literally blow the galaxy's gas reservoir clean out into intergalactic space, or it can heat the remaining gas to such incredibly high temperatures that it can no longer collapse to form stars. It's a catastrophic case of cosmic feedback. The very engine that helped build the galaxy eventually becomes the weapon that sterilizes it. The second suspect is an external threat, a violent galactic interaction. When galaxies swing too close to each other or collide, the gravitational chaos can be so extreme that it strips gas away, flinging it out into the vast voids between galaxies. Alternatively, a galaxy moving at high speed through the dense gas in the center of a galaxy cluster can have its own gas supply ripped away by a process called ram pressure stripping, much like the wind can blow the hat right off your head. The galaxy is left gasping for fuel, its star-forming potential extinguished in a relatively short cosmic timescale. The result is the same, a quenched galaxy. It becomes a zombie, a ghost of its former self. It's still there, its ancient stars continuing their slow, steady burn for trillions of years, but it is no longer alive in the dynamic sense. It's a fossilized snapshot of a past era, a beautiful but tragic monument to a creativity that has been permanently shut down. This process is ongoing right now all across the universe, a silent reminder that even the largest structures in the cosmos are subject to a cycle of life and death. Yet despite the silent graveyards of quenched galaxies that populate the cosmos, our most powerful telescopes are also time machines, allowing us to peer back to an era of incredible vitality and witness the very dawn of galactic light. The current record holder for this ultimate deep field observation is a galaxy known as GNZ11. The name might sound like a boring catalog entry, but the reality it represents is nothing short of breathtaking. When the Hubble Space Telescope first detected its faint, redshifted glow, astronomers realized they were looking at the most distant, and therefore the oldest galaxy ever seen by human eyes. The light from GNZ11 has been traveling across the universe for over 13.4 billion years to reach us. This means we are not seeing this galaxy as it is today, but as it existed a mere 400 million years after the Big Bang itself. To fully appreciate how stunningly early this is, we need to rewind the cosmic timeline. The Big Bang wasn't an explosion in space, but the rapid expansion of space and time from an infinitely hot, dense point. In the immediate aftermath, the universe was a searing, opaque soup of fundamental particles, too hot for light to travel freely. After about 380,000 years, it had expanded and cooled enough for atoms to form, allowing the first photons to finally stream across the universe in what we now detect as the cosmic microwave background. This was the universe's dark ages, a period without any stars or galaxies to light it up. gravity had to slowly, painstakingly pull together the first clumps of dark matter and gas to build the structures that would eventually become stars and galaxies. The fact that we can see a fully formed galaxy just 400 million years after this dark period ended is like finding a sophisticated, bustling city built on a landscape that was pure wilderness just a few decades before. But the truly insane part of GNZ 11 isn't just its age, it's what it is. This isn't a faint, primordial speck struggling to ignite its first few stars. This is a galaxy that, in its youth, was already a brilliant cosmic powerhouse. Observations suggest it was about 25 times smaller than our Milky Way, yet it was forming stars at a rate 20 times faster. It already contained around 1 billion stars and was shining with an intense ultraviolet brilliance. This is the core of the mystery that has astronomers rethinking their models. How did a galaxy grow so massive, so bright, and so mature in what amounts to a cosmic blink of an eye? Our best theories of hierarchical galaxy formation suggest that the universe started small. Tiny dark matter halos merged to form larger ones, which then attracted gas to form the first stars and protogalaxies. These small building blocks then merged over hundreds of millions of years to create the larger galaxies we see later on. GNZ 11 short-circuits this entire idea. It suggests that the early universe was far more efficient and rapid at building large structures than we ever thought possible. Somehow, vast reservoirs of gas collapsed directly and violently to form a substantial galaxy in a phenomenally short amount of time, skipping many of the intermediate steps our models predict. It forces us to ask, did we get the timeline of cosmic dawn completely wrong? Or are there unknown physical processes at work in the early universe that allowed for such explosive and precocious growth? This single, faint smudge of light is a monumental challenge to our understanding of cosmic evolution, a beacon from the edge of time that is pushing the limits of what we thought was possible. If the formation of the very first galaxies represents a cosmic birth, then the life that follows is governed by a much more brutal set of rules. We often picture galaxies as isolated, tranquil islands drifting peacefully through the void. The reality is far more dynamic and, frankly, far more savage. Galaxies exist in a state of constant gravitational competition, and the primary way the biggest ones grow to such immense sizes is not by creating new stars from scratch, but by consuming their smaller neighbors in an act of cosmic predation known as galactic cannibalism. This isn't a rare or exotic event. It is the standard mechanism of growth in the universe, and our own Milky Way is a prime example of a galaxy with a voracious appetite. To understand how this works, imagine the universe's largest galaxies as gravitational sharks, constantly circling within a school of smaller, weaker fish. A large galaxy's immense gravitational field creates a powerful pull that extends far beyond its visible disk of stars. When a smaller, dwarf galaxy ventures too close, it doesn't just get a tug, it gets completely unraveled. The force of gravity is stronger on the side of the dwarf galaxy facing its giant predator than on the side facing away. This difference in pull, known as a tidal force, stretches and distorts the smaller galaxy, pulling it apart like cosmic taffy over hundreds of millions of years. Its stars, gas, and dark matter are slowly stripped away and absorbed into the larger galaxy's halo, adding to its mass and size. The larger galaxy literally eats the smaller one, digesting its material to fuel its own expansion. We don't have to look far to see this process in action. Our very own Milky Way is currently in the midst of several such meals. One of the most dramatic examples is the Sagittarius dwarf spheroidal galaxy. Discovered in 1994, this tiny galaxy is caught in a death spiral around the Milky Way. It's believed it has already orbited our galaxy at least 10 times, and with each pass, our galaxy's tidal forces have torn more stars away from it. Today, it is a mere shadow of its former self, stretched into a long, looping stream of stars that completely encircles the Milky Way. it is being cannibalized in real time, and its remains are being woven into the very fabric of our galaxy's history. The most insane and beautiful evidence of this ongoing feast isn't found by looking at a single point of light, but by mapping the entire sky. Astronomers, using powerful digital sky surveys, have discovered these faint, ethereal structures known as stellar streams. They appear as long, thin, river-like formations of stars flowing in great arcs across the heavens. These are the galactic fossils we've been searching for, the ghostly remains of completely devoured dwarf galaxies. They are the smear of stars left behind after the tidal disruption is complete, a permanent scar on the sky that marks the site of an ancient cosmic consumption. The Milky Way is surrounded by them. We've identified dozens of these streams, each one the final testament of a galaxy that was consumed and digested. This process fundamentally changes our understanding of a galaxy's identity. The Milky Way was not born 100,000 light-years across. It started its life much smaller and has grown to its current majestic size by consuming perhaps 100 smaller galaxies over billions of years. The stars you see in the night sky aren't all native to our galaxy. A significant number of them are immigrants, stolen from other systems and adopted into our own. This means that galactic cannibalism isn't just a destructive force, it's also a creative one. The influx of fresh gas from these consumed galaxies can trigger new waves of star formation, and the merger itself can stir up the galactic disk, reshaping its structure. Our home galaxy is not a pristine, isolated entity. It is a cosmic melting pot, a hybrid built from the remains of countless others, a testament to the fact that in the grand theater of the universe, the largest structures are built from the ruins of the small. This idea of galactic cannibalism reveals a universe governed by fierce competition. But if we could zoom out far beyond any single galaxy or cluster, we would see that this struggle for growth is all happening within a structure of breathtaking order and scale. For centuries, we imagined the cosmos as a vast, dark ocean with galaxies scattered randomly like lonely ships adrift in the night. This intuitive picture is completely wrong. The large-scale structure of the universe is not random, not scattered, and certainly not empty. Instead, galaxies are arranged in the single most immense and intricate architecture conceivable, an enormous cosmic web. This web is built from unimaginably long filaments of dark matter, each 1 millions of light-years in length. These filaments act like invisible cosmic highways, tracing the underlying gravitational blueprint of the universe. Where these filaments intersect, they form immensely dense nodes. These are the great clusters of galaxies, the bustling metropolitan centers of the cosmos, each containing thousands of galaxies bound together by gravity. And surrounding these great clusters and connecting filaments are the opposite, of vast, empty, and deeply mysterious regions known as cosmic voids. These are the universe's true deserts, incomprehensibly large volumes of space that are almost completely devoid of both matter and galaxies. The scale of a single void can be so immense that light would take hundreds of millions of years to travel from one side to the other. This creates a universe that looks, on the grandest scale, like a sponge or a network of neurons, a delicate balance of dense, bright structures and profound, empty darkness. This cosmic web didn't form by accident. It is the direct result of the initial conditions of the Big Bang. In the earliest moments, the universe was almost perfectly uniform, but not quite. Tiny quantum fluctuations, smaller than a single atom, were imprinted onto the fabric of space-time. As the universe expanded over billions of years, gravity acted as a cosmic amplifier, relentlessly pulling matter, both the dark matter we can't see and the normal matter we can, toward those slightly denser regions. The dark matter formed the invisible skeleton of the web first, and normal matter then flowed along these gravitational channels, eventually collapsing to form the galaxies we observe today, perfectly outlining the dark matter architecture. Understanding this web forces us to completely redefine our own cosmic address. We are not just in the Milky Way, which is part of a local group of galaxies, which is itself part of the Virgo cluster. All of this is merely a small part of something far grander, the Laniakea supercluster. This Hawaiian name translates beautifully to immense heaven, and it is a fitting title for a gravitational domain containing over 100,000 individual galaxies, including our own. The Laniakea supercluster spans an almost inconceivable 500 million light-years. To grasp that scale, remember that a single light-year is 9.5 trillion kilometers. Multiply that by 500 million, the numbers become meaningless to the human mind. We can only stand in awe of the sheer volume of space this structure commands. Our place within Laniakea is not at the center, but out on one of its great, sprawling filaments, like a suburban neighborhood on the outskirts of a vast metropolis. And just like water always flows downhill, our entire supercluster, all 100,000 galaxies, is drifting in a slow, cosmic river towards a single, mysterious point in space. Astronomers call this gravitational focal point the Great Attractor. It represents a concentration of mass so immense that it pulls on everything in our corner of the universe. For decades, the Great Attractor remained one of astronomy's great mysteries because it lies in the zone of avoidance, an area of the sky hidden from our view by the dense stars and dust of the Milky Way's own disk. We were essentially trying to study something hidden behind a cosmic curtain. Modern observations in X-ray and radio wavelengths have allowed us to peer through that dust, revealing that the Great Attractor is not a single, unimaginable object, but rather the collective gravitational pull of an enormous overdensity of mass, likely the core of the Laniakea supercluster itself, dominated by a massive cluster of galaxies known as the Norma cluster. This region, while incredibly dense, is still part of the natural structure of the cosmic web. Our entire local universe is flowing towards this gravitational valley, this deep well in the fabric of space-time. This grand motion reminds us that even the mightiest structures we can see are themselves subject to forces far larger than themselves, all moving in a silent, stately dance choreographed by gravity billions of years ago. We are not just on a planet orbiting a star in a galaxy. We are part of a supercluster flowing on a filament in a web that spans the entire observable universe. That sense of a grand, orderly web is humbling, but it barely prepares us for what is perhaps the most staggering numerical fact in all of astronomy. For centuries, the question of just how many galaxies exist was a subject of pure speculation. Even with the advent of powerful telescopes, our view was limited. Then, in the 1990s, the Hubble Space Telescope performed an experiment that would forever change our perspective. Astronomers pointed Hubble at a seemingly empty patch of sky, a dark region no larger than a grain of sand held at arm's length. They left the shutter open for what became known as the Hubble Deep Field, collecting faint light for over 100 consecutive hours. What came back was not darkness. That tiny, insignificant point was filled with not dozens, but thousands of distinct galaxies, each one an entire island universe of its own. By repeating this experiment in different parts of the sky, astronomers were able to extrapolate a census for the entire observable universe. The number they arrived at is so vast, so fundamentally incomprehensible, that it challenges the very limits of human intuition. The current best estimate is that there are at least 2 trillion galaxies in the observable universe. Let's sit with that number for a moment, 2 trillion. That is a 2 followed by 12 zeros. To even begin to visualize such an amount, consider this famous analogy. Go to any beach on Earth and scoop up a single handful of sand. Count the individual grains in your hand. Now, imagine that for every single one of those tiny grains, there are 10,000 entire galaxies out there in the cosmos. The number of galaxies in the universe dwarfs the number of sand grains on every beach, in every desert on our entire planet. It is a scale of such profound magnitude that it can only be felt, not truly understood. This number represents a universe of almost limitless possibility, a canvas so large that it defies any attempt to call it empty or lonely. But the truly insane part of this story is that 2 trillion is almost certainly an undercount. This number is based on what we can observe now. The universe is dynamic and it has been evolving for 13.8 billion years. In the ancient past, the population of galaxies was even more dense and numerous. The early universe was a crowded place, filled with a far greater number of smaller, fainter protogalaxies. Over the eons, the relentless force of gravity took its course. These smaller galaxies, drawn together by their mutual attraction, began to merge. This process of hierarchical growth, of cosmic cannibalism on a universal scale, is how the larger, majestic galaxies we see today, the spirals and ellipticals, were assembled. Countless dwarf galaxies were consumed, their identities lost to history, absorbed into the larger structures we now observe. So while we can see 2 trillion galaxies today with our most powerful instruments, the total number of galaxies that have ever existed throughout the history of the universe is a number that is, quite literally, unimaginably larger. It's a haunting thought. We are not only living in a universe of immense scale, but we are also seeing it at a relatively mature stage in its life, long after its most vibrant and populous era has already passed. The night sky appears dark to our eyes not because space is empty, but because the light from billions upon billions of additional galaxies is too faint, too redshifted, or has been erased by the expansion of the universe itself. The darkness is an illusion, hiding a past brimming with even more light. And just as these vast structures are defined by gravity and dark matter, they are also shaped by another, far more subtle force, one that is incredibly faint but undeniably present. It's a fact that often gets overlooked in the grand tale of galaxies. They have their own magnetic fields. Now, we're used to thinking about magnetism on a small scale, like the powerful pull of a fridge magnet. But the idea that an entire galaxy, a swirling collection of hundreds of billions of stars, could be magnetized seems almost like science fiction, yet it is absolutely true. These galactic magnetic fields are woven through the entire interstellar medium, running along the spiral arms and stretching across the vast voids between the stars. They are, however, almost unimaginably weak. A typical galactic magnetic field is millions of times weaker than that common household magnet. Detecting a force that faint across such immense distances is one of the greatest technical challenges in all of modern astronomy. So how do we even know they are there? We can't see magnetism directly, but we can observe its effects on the things we can see. As electrons and other charged particles travel through these vast magnetic fields, they are forced to spiral along the field lines. This spiraling motion causes them to emit a specific kind of radiation known as synchrotron radiation, which we can detect with radio telescopes. By mapping this faint radio glow, astronomers can literally trace out the invisible magnetic architecture of a galaxy. In some cases, we can even see the field's orientation by observing how it polarizes the light from distant stars, making them appear to glow in a specific direction. These painstaking observations reveal that magnetic fields are not random or chaotic. They are often remarkably organized, following the grand design of the spiral arms themselves, as if the galaxy has a subtle magnetic skeleton running through its very bones. These fields are far from being a simple cosmic curiosity. They play an active and crucial role in the life cycle of a galaxy. Think about the process of star formation. It begins when a massive cloud of gas and dust collapses under its own gravity. But without magnetic fields, this collapse would be almost instantaneous and wildly inefficient. The magnetic fields threading through these clouds provide a form of support, a counter-pressure that slows down the collapse, allowing the cloud to fragment in a more orderly way and ultimately governing the birth of stars. They act as cosmic regulators, ensuring that stars form at a sustainable pace rather than in a single, frantic burst. Furthermore, These magnetic fields are essential for guiding and containing cosmic rays, high-energy particles, mostly protons, that race across the galaxy at nearly the speed of light. Without magnetic fields to corral them, these rays would simply fly off into intergalactic space. Instead, the fields trap them, bending their paths and keeping them whirling around within the galaxy for millions of years, creating a pervasive sea of high-energy radiation that is a fundamental part of the galactic ecosystem. But this leads us to one of astronomy's most perplexing unsolved mysteries. Where did these immense magnetic fields originally come from? We understand how a dynamo works on a planet like Earth. The convection of molten metal in the outer core, combined with the planet's rotation, generates and sustains our magnetic field. But a galaxy has no solid core, no simple engine to power such a thing. The leading theory, known as the galactic dynamo theory, suggests that the weak magnetic fields of the early universe were somehow amplified by the turbulent motions of ionized gas within the galaxy. As the galaxy rotates and its gas swirls, these motions could stretch, twist, and fold the magnetic field lines, transferring the energy of turbulent motion into magnetic energy, effectively making the field stronger over billions of years. It's a compelling idea, but it has a major flaw. It requires a seed magnetic field to amplify in the first place, and the origin of those primordial seed fields is a complete mystery. Did they emerge from processes in the ultra-early universe just moments after the Big Bang? Or were they first generated by the first generations of stars or even black holes? We simply do not know. The fact that we can detect and map these faint forces yet still cannot explain their fundamental origin is a beautiful reminder that even the most subtle elements of the cosmos can hold some of its deepest secrets. Yet even within the organized structure of the cosmic web and the subtle influence of magnetic fields, galaxies can sometimes act with startling violence, hurling their own stars out into the eternal darkness. We tend to think of stars as permanent, fixed residents of their galactic homes, orbiting peacefully for billions of years. But the universe has a way of breaking the rules, creating cosmic projectiles through gravitational chaos. These events give rise to what astronomers call hypervelocity stars, lone suns shot out of their galaxies at speeds so immense they become eternal exiles. The most common way this happens is within the incredibly dense, bustling environments at the very hearts of galaxies. Picture a star cluster near the supermassive black hole, where the gravitational pull is unimaginably strong and stars are packed together like commuters in a rush-hour crowd. In this celestial mosh pit, complex gravitational dances are constantly playing out. Sometimes a binary star system, two stars orbiting each other, will wander too close to the central black hole. The black hole's immense gravity can violently disrupt this partnership. In a gravitational slingshot effect, one star might be captured into a tight orbit around the black hole, while its companion is flung away at an astonishing velocity, a speed that can exceed 2 million miles per hour. At that incredible rate, the ejected star isn't just moving fast, it achieves something truly extraordinary: escape velocity. This is the critical speed needed to break free from the gravitational bonds of its entire home galaxy. In an instant, this star is transformed from a member of a vast community into a solitary wanderer. It punches through the outer halo of dark matter and shoots out into the intergalactic void, the vast and nearly empty space between galaxies. It becomes a true runaway, destined to never return. The trajectory of these stars is a one-way ticket into nothingness. For billions of years, a hypervelocity star will drift through this profound darkness, completely isolated. If you could stand on a planet orbiting such a star, the view would be both spectacular and deeply lonely. The night sky would be dominated by the faint, receding glow of its home galaxy, slowly shrinking into just another faint smudge of light among countless others. There would be no nearby stars to provide companionship, no glowing nebulae to light up the darkness, just the cold, empty blackness of intergalactic space. These stars are the ultimate loners of the cosmos, cast out from their birthplace to live out their lives in utter solitude. The existence of these stellar exiles provides astronomers with a unique and powerful tool. By tracing the path of a hypervelocity star backward across the sky, they can actually map the gravitational field of the galaxy it came from, including the distribution of its invisible dark matter halo. These runaway stars are like cosmic probes sent out on involuntary missions to help us understand the very forces that expelled them. They are a breathtaking reminder that even in a universe governed by immense structures and collective motion, the individual can still be launched on a journey of unimaginable scale and isolation. And just when we thought we were beginning to understand the rules, the universe delivered a discovery so bizarre it threatened to unravel our entire model of cosmic structure. For decades, the existence of dark matter was the only thing that made sense of what we observed. It was the invisible glue holding galaxies together, the essential ingredient without which the universe as we see it simply couldn't exist. But then, in 2018, astronomers made an observation that turned this fundamental belief on its head. They found a galaxy that, by all accounts, shouldn't be there at all. Its name is NGC 1052DF2, and it is a cosmic paradox, a galaxy that appears to contain virtually no dark matter. The discovery was so shocking that the initial reaction among the scientific community was one of profound skepticism. The lead researcher, Pieter van Dokkum of Yale University, even stated that they essentially spent a full year trying to kill the result, searching for any possible error in their methods or assumptions. But the evidence held firm. This galaxy, located about 65 million light-years away, is a peculiar type known as an ultra-diffuse galaxy. It's large, about the size of our Milky Way, but it is incredibly sparse, containing only around 1/200th of the number of stars. To measure its mass, astronomers used two independent methods. First, they measured the motions of 10 bright star clusters within the galaxy. In a typical galaxy, these clusters would be whizzing around at high speeds, held in check by the powerful gravitational grip of the unseen dark matter halo. But in NGC 1052DF2, the clusters were moving surprisingly slowly, just fast enough to be held by the gravity of the visible stars themselves. The second method involved studying the galaxy's total starlight and using that to estimate the mass of its stars. Both methods pointed to the same incredible conclusion. The mass you could see was almost exactly the mass that was there. There was no room left for dark matter. This single observation has monumental implications. For years, a small but vocal group of physicists had proposed alternative theories to dark matter, suggesting that instead of an invisible particle, we simply don't understand gravity correctly on large scales. They proposed modified laws of gravity known as MUND that could potentially explain the rotation curves of galaxies without needing any extra matter. But the existence of NGC 1052DF2 is a fatal blow to those ideas. If our understanding of gravity were wrong in a way that made dark matter unnecessary, then every galaxy should behave as if it has dark matter. You cannot have a modified law of gravity that just selectively stops working for one specific galaxy. The fact that this one galaxy has no dark matter, while nearly every other one does, is the strongest evidence we have that dark matter is not a flaw in our theories. It is a real, physical thing, a substance that can be present or absent. It proves that dark matter is separable from normal matter. This raises an even deeper and more fascinating mystery. How did this galaxy form in the first place? Our standard model says galaxies begin their lives as clumps of dark matter that attract gas, which then cools and forms stars. Without that dark matter seed, a structure this large shouldn't exist. One compelling theory is that NGC 1052DF2 is the result of a catastrophic galactic collision. Perhaps it was once a more typical galaxy, but it had a violent encounter with a much larger neighbor. In this scenario, the gravitational tides could have ripped away not only its stars and gas, but also its dark matter halo, leaving behind the wispy, disembodied galaxy we see today. Another theory suggests it formed in a unique way from gas that was ejected during a massive galactic merger, gas that was heated and stripped of its dark matter before it later collapsed to form stars. Whatever the cause, its very existence forces us to broaden our imagination. Galaxies are not all built the same way. The universe, in its infinite creativity, has more than one recipe for building an island of stars, and we are only just beginning to read the cookbook. This ghostly, enigmatic galaxy is a powerful reminder that for every rule we think we've uncovered, the cosmos is ready with a brilliant, beautiful exception. This brings us to one of the most pivotal and genuinely insane observations in all of astronomy, a celestial behavior so baffling that it forced scientists to invent an entirely new branch of physics to explain it. It's known as the galaxy rotation problem, and it all starts with a very simple, very reasonable expectation based on the laws of gravity we've understood for centuries. Think about our own solar system for a moment. It's a perfect, elegant demonstration of how gravity works on a grand scale. The Sun, as the most massive object, sits at the center, and all the planets orbit around it. But they don't all orbit at the same speed. Mercury, the closest planet, zips around the Sun at a blistering 47 kilometers per second. Out where Neptune orbits, far from the Sun's gravitational grip, the planet moves at a much more leisurely pace of just 5.4 kilometers per second. This makes perfect sense. The farther you get from the central mass, the weaker the gravitational pull, and the slower an object needs to move to maintain a stable orbit. This pattern is a fundamental prediction of Kepler's laws and Newtonian physics. We expected this same rule to apply on a much larger scale to entire galaxies. So, when astronomers in the 1970s, like Vera Rubin and Kent Ford, began meticulously measuring the orbital velocities of stars in distant spiral galaxies, they expected to see a clear and steady decline. Stars near the bright, dense center should be orbiting very fast, pulled by the immense collective gravity of all the stars, gas and dust packed together there. But as you moved your gaze outward toward the galaxy's sparse and dim outskirts, the orbital speeds of those stars should have dropped off dramatically. The data, however, told a completely different and utterly confounding story. What they found, and what has since been confirmed in galaxy after galaxy after galaxy, is that the orbital speed of stars does not drop off. Once you get past the central bulge, the rotation curve, the graph that plots a star's orbital speed against its distance from the center, does something astonishing. It flattens out. Stars on the very outer fringes of a spiral galaxy, tens of thousands of light years from the center, are whipping around at nearly the same high speed as those stars much closer in. This is the flat rotation curve, and it is a direct violation of what the visible mass of the galaxy says should happen. According to all the observable matter, the stars and the gas we can see, those outer stars should be moving so slowly that the galaxy's own gravity wouldn't be strong enough to hold onto them. They should have been flung off into the intergalactic void long ago, leaving the galaxy to simply disintegrate. The fact that they aren't, the fact that these galaxies are stable, means only one thing: our inventory of the universe is catastrophically incomplete. There had to be something else there, something we couldn't see. A tremendous amount of extra mass must be providing the additional gravitational muscle to keep those outer stars moving at such breakneck speeds. This invisible mass couldn't be concentrated in the center like the stars. Its gravitational influence had to be felt most strongly out in the galactic suburbs, meaning it had to be distributed in a massive, spherical halo that extended far, far beyond the visible edge of the galaxy itself. This was the first direct, incontrovertible evidence for the existence of dark matter. It wasn't a hypothesis born in a theoretical vacuum. It was a solution demanded by the hard, cold, observational data. The universe was literally showing us through the motion of its stars that the majority of its matter was of a form completely unknown to science. This discovery was a monumental paradigm shift, a humbling lesson in cosmic humility. It was an insane reminder that our senses and even our most advanced telescopes are deeply limited. We experience the world and the universe through light, but most of the universe does not play by those rules. What we see is a mere decoration, a glittering trim on the edges of a far vaster, darker, and more massive underlying structure. The true cosmos is built from a shadow framework, and the motions of the stars are just the visible tracer lines allowing us to finally map its invisible shape. But if the motion of stars within a single galaxy points to an invisible framework, then the collective behavior of thousands of galaxies reveals a structure of such immense power that it literally bends the cosmos. We've been exploring the incredible nature of individual galaxies, but they are rarely truly alone. Just as stars gather into galaxies, galaxies themselves gather into the largest gravitationally bound structures in the entire universe, galaxy clusters. These are not just random collections, they are the bustling metropolitan centers of the cosmos, and their scale and energy defy all earthly comparison. A typical large cluster can be home to thousands of individual galaxies, all swarming around a common center of gravity. The space between these galaxies is anything but empty. It is filled with a superheated, tenuous gas known as the intracluster medium. This plasma is so incredibly hot, reaching temperatures of tens of millions of degrees, that it doesn't emit visible light. Instead, it glows with the most energetic form of light, X-rays. This means if our eyes could see in X-ray vision, the night sky near a cluster would be dominated by a colossal, diffuse cloud of brilliant light, a fog of energy that contains more normal matter than all the thousands of galaxies within the cluster combined. The insane energy source heating this gas is the immense gravitational pull of the cluster itself. As gas falls into the cluster's gravitational well, it gains tremendous speed, and that motion is converted into heat, creating a perpetual cosmic furnace. Yet, even this superheated plasma is only a small part of the story. The true anchor of a galaxy cluster, the reason it can exist at all, is its mind-bogglingly massive halo of dark matter. This invisible scaffolding provides the gravitational glue that holds the entire chaotic structure together. The combined mass of a large cluster is so stupendous that it doesn't just attract matter, it warps the very fabric of space-time around it, in accordance with Einstein's theory of general relativity. This warping creates an effect so extraordinary it seems like magic. The cluster becomes a gravitational lens. A gravitational lens acts like a faulty but incredibly powerful cosmic magnifying glass. When light from a distant background galaxy travels toward us and passes through this warped region of space, its path is bent. This can distort the image of the background galaxy into spectacular arcs and rings of light, like looking at a street lamp through the bottom of a wine glass. In some cases, it can magnify the distant object, allowing us to see galaxies that would otherwise be far too faint and remote for any telescope to detect. This natural telescope gives astronomers a powerful tool to peer deeper into the universe than ever before, but it also provides the most direct way to weigh these colossal clusters. By measuring how severely the light is bent, we can calculate the total mass causing the distortion, and time and again, the result confirms that what we can see, the thousands of galaxies and the hot gas, accounts for only a small fraction of the total mass. The overwhelming majority is yet again the invisible hand of dark matter, sculpting the universe on its grandest scale. But the gravitational chaos of galactic mergers doesn't just create stellar streams and reshape spiral arms. It can forge something even more bizarre and visually striking at the very heart of a galaxy. We often imagine a galactic center as a single, powerful engine, a lone supermassive black hole anchoring the entire structure. Yet, the universe has a flair for the dramatic, and through violent collisions, a galaxy can be left with not one, but multiple brilliant nuclei shining in its core. This isn't a temporary glitch, it's a direct snapshot of a cosmic merger caught in the act, a celestial dance of unimaginable power and scale. The most insane and beautiful example of this phenomenon is a galaxy known as Markarian 315. When astronomers first trained their telescopes on it, they didn't see a single, unified center. Instead, they found two intensely bright nuclei staring back at them, separated by a gap of about 15,000 light-years. To put that distance in perspective, that's nearly 1/5 the distance from our Sun to the center of the Milky Way. These are not just two random clumps of stars, they are the former hearts of two distinct spiral galaxies, each with its own supermassive black hole, now locked in a slow, gravitational embrace within their new, combined home. This incredible structure is the direct result of a head-on collision that occurred hundreds of millions of years ago. As the two galaxies swung through each other, their vast clouds of interstellar gas and dust were violently compressed, triggering a firestorm of new star formation. But their cores, bolstered by the incredible inertia of their supermassive black holes, resisted an immediate merger. Instead, they began a long, slow orbital dance around a common center of gravity. What we are witnessing is the aftermath of that impact, the two former galactic cores now orbiting each other, each one still actively feeding on the surrounding gas and shining with the ferocious intensity of a quasar. This double nucleus is more than just a spectacular sight. It's a preview of a far more colossal event that will unfold over billions of years. The two supermassive black holes, each weighing millions of times the mass of our Sun, are now bound together. As they orbit, they will gradually lose energy through gravitational waves and through dynamical friction, a process where they plow through the surrounding sea of stars and gas, slowing down like a ship moving through water. This slow loss of energy will cause their orbits to decay, drawing them closer and closer together over an almost incomprehensible timescale. Eventually, in the far distant future, these two behemoths will merge, releasing a titanic burst of gravitational waves that will ripple through the very fabric of spacetime itself. This event will create a single, even more monstrous black hole, a true leviathan that will anchor the new, combined galaxy for the rest of its existence. Markarian 315 offers us a rare and precious glimpse into this prolonged cosmic process. Most galactic mergers are seen either before the collision, when the galaxies are still separate, or long after, when the merger is complete and the evidence has been smoothed away by time. To see a galaxy with two distinct, active hearts is to catch the universe in a fleeting moment of creative destruction, a temporary and unstable phase that reveals the incredible forces that continually build and reshape the cosmos. This concept of deep cosmic time brings us to a rhythm that governs our very existence, a celestial heartbeat so slow that its full measure spans hundreds of millions of years. We mark our lives by the Earth's rotation, our years by its orbit around the Sun, but our solar system itself is on a far grander journey. Our Sun, along with all its planets, moons, and asteroids, is not stationary. It is an eternal traveler, orbiting the supermassive black hole at the heart of the Milky Way at a breathtaking speed of over 200,000 kilometers per hour. Despite that incredible velocity, the sheer scale of our galaxy is so immense that a single complete orbit takes the solar system approximately 225 to 250 million years. This staggering period of time is known as a galactic year or a cosmic year, and it provides perhaps the most humbling calendar imaginable. To truly appreciate the scale of a galactic year, we need to anchor it in Earth's own history. The last time our solar system was in this particular position in its galactic orbit, the Earth looked utterly alien. It was the late Triassic period. The supercontinent of Pangaea was just beginning to break apart. The earliest dinosaurs were taking their first tentative steps, and the ancestors of mammals were small, shrew-like creatures hiding in the shadows. A single galactic year encompasses the entire reign of the dinosaurs, their catastrophic extinction, the rise of mammals, and the eventual emergence of humanity. All of that profound biological change fits into just one tick of the galaxy's clock. Now consider the age of our Sun itself, which formed roughly 4.6 billion years ago. If we do the math, that means our star has completed only about 20 full orbits around the galactic center. The entire multi-billion-year history of our solar system, from its chaotic birth in a primordial cloud of gas and dust to the stable system we know today, has occurred in just 20 galactic years. Every mountain range that has risen and eroded on Earth, every extinction event and evolutionary explosion, has happened within the span of these 20 loops. This perspective reaches its most dizzying extreme when we consider human history. All of recorded civilization, from the construction of the first ancient cities to our modern technological society, has unfolded in less than 1,000th of a single galactic year. If we were to compress the entire 250 million-year orbit into a single 24-hour day, then the entirety of human civilization from agriculture to astronomy would flash by in the last quarter of a second before midnight. We are living in a moment so fleeting, so infinitesimally small on the cosmic scale, that it defies human comprehension. It reminds us that our time here is precious and brief, a single, bright note in a symphony of almost unimaginable duration. Yet for all the ingenuity required to find them, the true insanity of these dark galaxies lies not in their discovery, but in their incomprehensible composition. The poster child for this cosmic enigma is a galaxy known as Dragonfly 44, located in the Coma cluster about 330 million light-years away. At first glance, it seems utterly unremarkable, a faint, blurry smudge of light. But when astronomers measured its mass, they were met with a result so bizarre it defied all logic. Dragonfly 44 has roughly the same mass as our entire Milky Way galaxy. You would expect an object with that much gravitational heft to be a brilliant pinwheel of a trillion stars. But Dragonfly 44 is not. It contains only a tiny fraction of the stars we have, perhaps 1%, and as a result, it emits less than 1% of the light. This means that if the Milky Way is a bustling, luminous metropolis, Dragonfly 44 is a ghost town of the same physical size, with only a few flickering streetlights to suggest it exists at all. Where did all that mass go if not into stars? The answer is the most extreme example of dark matter dominance ever observed. Calculations show that a staggering 99.99% of Dragonfly 44's mass must be in the form of this invisible substance. This galaxy isn't just made of dark matter, it is, for all intents and purposes, almost exclusively dark matter. It is a cosmic paradox, a galaxy-sized amount of mass that has almost entirely failed to turn itself into the stars and planets that we normally think of as a galaxy. It's as if the universe set out to build a galaxy but forgot to include the luminous parts, leaving behind a pure, massive halo of dark matter with only a whisper of stellar decoration. This raises a profound and unsettling question. How does something like this even form? Our standard models of galaxy formation are built on the idea that dark matter halos act as gravitational seeds, pulling in gas that then cools and fragments to form stars. Dragonfly 44 clearly had a massive dark matter seed, but for some reason, the star-forming process almost completely failed. Perhaps its gas was stripped away early on by the harsh environment of the galaxy cluster it resides in, or maybe the gas was simply too hot to collapse and form stars in the first place. Whatever the cause, its existence proves that the universe can assemble structures of immense scale that remain almost entirely in the shadows, forever hidden from our view. But what if a galaxy's central engine doesn't just simmer quietly or regulate gently? What if it ignites into the single most powerful and violent sustained energy source in the entire known universe? This brings us to the truly explosive side of galactic cores, a phenomenon so intensely brilliant it can redefine the word power. At the heart of some galaxies, the supermassive black hole doesn't just snack on passing gas. It enters a state of insatiable, gluttonous feasting, transforming the core into what astronomers call an active galactic nucleus, or AN. This isn't just a bright spot, it's a cosmic hurricane of energy, a maelstrom where physics is pushed to its absolute limits. The engine of this fury is the accretion disk. When a vast amount of gas, dust, or even entire stars is funneled toward the black hole, it doesn't just fall in. Conservation of angular momentum forces it to flatten into a spinning disk, a whirlpool of doomed matter circling the drain of the event horizon. The particles within this disk are moving at velocities approaching the speed of light, creating unimaginable friction and tidal forces. This superheats the material to millions of degrees, causing it to glow with a blinding intensity across the entire electromagnetic spectrum, from radio waves to gamma rays. The energy released in this process is so prodigious that it can outshine the combined light of every single star in the host galaxy. Not by a little, but by a factor of 1,000 or more. The black hole's dining room becomes the brightest single object for millions of light years in every direction. The most extreme and luminous class of these objects are known as quasars, short for quasi-stellar radio sources. When first discovered, they appeared as star-like points of light in optical telescopes, but their radio emissions and incredible redshifts revealed their true, monstrous nature. A single quasar, powered by a black hole consuming perhaps the mass of our Sun every single day, can be so bright that it drowns out the light of its entire host galaxy, making the hundreds of billions of stars that built it virtually invisible by comparison. These are the beacons of the early universe, visible from the farthest cosmic distances, their light serving as a testament to an era when galaxies were younger, gas-rich, and their central black holes fed with reckless abandon. Yet the raw light is only part of the story. The true signature of an AGN's insanity often manifests in colossal, focused jets that erupt from the poles of the system. Not all the material in the accretion disk falls inward. Some of it, energized by powerful magnetic fields that are wound up by the disk's rotation, is channeled and blasted outward at nearly the speed of light. These jets of charged particles can extend for millions of light years, far beyond the confines of their host galaxy, punching into the intergalactic medium. We can detect these jets because the particles within them emit synchrotron radiation as they spiral along magnetic field lines, creating brilliant, often radio-loud, lobes that mark the jet's terminating shock wave. The impact of these jets is anything but cosmetic. They are a dominant feedback mechanism that shapes galactic evolution. As these high-energy beams plow through the surrounding intergalactic and intracluster gas, they inject enormous amounts of energy and heat. This process can prevent the surrounding cool gas from collapsing to form new stars, effectively sterilizing vast regions of space. In this way, the AGN acts as a cosmic self-regulator. Its incredible outbursts, born from its own feast, ultimately shut down the very fuel supply that feeds it, putting a limit on its own growth and the growth of its host galaxy. It's a spectacular demonstration of a cosmic balancing act, where the most violent object in the galaxy becomes the key to maintaining equilibrium, proving that even in the deepest chaos, the universe has a way of enforcing its own order. But if we think of galactic evolution as a slow, stately process, we must also consider the dramatic events that can accelerate it. Events that unleash energies so profound they can sterilize entire regions of space. We've explored how galaxies grow through mergers and how their central black holes can regulate star formation, but there exists an even more extreme phenomenon, a galaxy-wide explosion of such staggering power that it can fundamentally alter a galaxy's destiny. This is not a collision or a quasar's jet, but something far more rare and catastrophic, a supermassive black hole that literally blows its own galaxy apart. The mechanism behind this incredible event is still a topic of intense research, but the leading theory points to a final, unimaginable feast. When two galaxies merge, their central supermassive black holes will eventually spiral together and coalesce. During this merger, vast reservoirs of gas can be funneled toward the newly formed single black hole, creating an accretion disk of unprecedented scale and density. Under these perfect storm conditions, the release of energy may become so extreme that it becomes unstable. Instead of being focused into jets, the energy might flood outwards in all directions as a spherical shockwave of incalculable force. This is not a directed beam, it is a true explosion, a detonation that erupts from the galactic core and propagates out through the entire galaxy at millions of miles per hour. The effect of such an outburst is nothing short of apocalyptic. This shockwave would blast through the galaxy's interstellar medium, the cool clouds of gas and dust that are the raw material for new stars. It would heat this gas to such incredibly high temperatures that it could never cool down and collapse again. In one violent, galaxy-wide event, the very fuel for future star formation is effectively vaporized and expelled into the intergalactic void. The galaxy's stellar nursery is permanently closed for business. What remains is a red and dead elliptical galaxy, but one that was quenched not through a slow strangulation but by a sudden, violent coup de grace. The black hole, in its moment of ultimate indulgence, effectively commits galactic suicide, severing the supply line that sustained it and ensuring that its host galaxy will never again know the spark of new birth. Evidence for these incredible events is etched into the sky, hidden in plain sight. Astronomers have discovered giant, spherical bubbles of extremely hot gas emanating from the cores of some galaxy clusters. These structures, often only visible in X-ray wavelengths, can span hundreds of thousands of light-years. They are thought to be the fossilized remnants of these ancient explosions, the ghostly imprint of a shockwave that expanded and then stalled, leaving a permanent cavity in the cluster's gas. Finding these bubbles is like finding the crater from a long-ago asteroid impact. It tells us that something profoundly violent happened here, even if the event itself is billions of years in the past. These cosmic fossils suggest that while such explosions are incredibly rare, they are a possible and ultimate fate for a galaxy, a final, dramatic act in the long and dynamic story of galactic life. But to truly grasp the distance these photons have traveled, we need to understand the single most important clue they carry: redshift. This isn't just a technical detail for astronomers, it's the universe's own way of writing its history and its expansion into the very light we see. The concept is rooted in a familiar earthly phenomenon, the Doppler effect. You experience this when an ambulance speeds past you. As it approaches, the sound waves are compressed, making the siren's pitch sound higher. As it moves away, the waves are stretched out, making the pitch sound lower. Light behaves in a remarkably similar way. When a source of light is moving away from us, the waves of light are stretched, which shifts them toward the red end of the spectrum. When we look at the vast majority of galaxies, we see this redshift telling us they are all rushing away from us. The startling revelation from this observation is that the universe itself is expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. Now, the truly insane part of this story is that for the most distant galaxies, this isn't just a slight reddening. The expansion of the universe over the billions of years that the light has been traveling stretches the very fabric of space itself, which in turn stretches the wavelength of the light journeying through it. The farther the light has to travel, the more space has expanded during its trip, and the more extremely the light is redshifted. For a galaxy like GNZ 11, the expansion is so profound that its ultraviolet light, which was emitted as a bright, energetic glow, has been stretched all the way into the infrared part of the spectrum by the time it finally reaches our telescopes. This is why missions like the James Webb Space Telescope are so revolutionary. They are specifically designed to see in the infrared, allowing them to catch this ancient, stretched light that is invisible to our eyes and to telescopes like Hubble. This leads us to the most profound implication of all, a concept that bends the mind every time we consider it. Because light has a finite speed, it takes time to travel any distance. When we look at the moon, we see it as it was 1.3 seconds ago. When we look at the sun, we see it as it was 8 minutes ago. And when we point our most powerful telescopes at a galaxy like GNZ 11, whose light has been traveling for 13.4 billion years, we are not seeing it as it exists today. We are seeing it as it was just 400 million years after the Big Bang. We are receiving a snapshot from the universe's infancy, a fossilized image carried by photons that began their journey before our planet, our sun, or even our galaxy had fully taken shape. That light is our only time machine, and by collecting it, we are piecing together the family album of the cosmos, watching the first generations of galaxies take their initial formative steps. It is a direct window into a past so remote that the universe was an entirely different place, and it allows us to test our theories of cosmic evolution by comparing what we predict should have been there with what we actually observe shining back at us from the edge of time itself. Yet even amidst the slow, majestic timelines of galactic orbits and the explosive feedback from black holes, there exists a phenomenon of such intense and focused creativity that it can redefine a galaxy in a spectacularly short cosmic burst. While many galaxies form stars at a steady, gentle pace, others experience a period of incredible, almost violent productivity known as a starburst. This is not just a slight uptick in activity, it is a frenzy of creation, a galaxy-wide firestorm where new stars are born hundreds or even thousands of times faster than in a placid spiral like our Milky Way. To appreciate the sheer intensity of a starburst, we need a point of comparison. Our galaxy is a relatively quiet stellar nursery, forming about 1 or 2 new stars per year on average. This is a sustainable rate, gently converting its reservoir of gas over billions of years. A classic starburst galaxy, however, operates on a completely different level. It can churn out stars at a rate of hundreds per year. This is not a gentle process, it is a veritable assembly line of stellar birth, operating at maximum capacity and burning through a galaxy's entire supply of star-forming fuel in a remarkably short period, sometimes in as little as 10 million years, a mere blink of an eye on the galactic timescale. This incredible burst of activity doesn't happen in a vacuum. It requires a powerful trigger, and the most common catalyst is a galactic collision or a very close gravitational encounter. When two galaxies swing past each other or plunge directly into one another, their mutual gravitational pull creates immense tidal forces. These forces act like a cosmic hand, violently squeezing and compressing the vast clouds of hydrogen gas that permeate both galaxies. This sudden compression is the key. It pushes the gas over a critical threshold, causing it to fragment and collapse under its own gravity at a ferocious rate, igniting the birth of millions of stars simultaneously all across the galactic landscape. The most stunning and well-studied example of this process is a pair of interacting galaxies known as the antennae galaxies, located about 45 million light-years away. When we look at them, we are witnessing a celestial car crash in slow motion. The name comes from the 2 long, streaming tails of stars and gas that have been flung out into space by the gravitational interaction, resembling the antennae of an insect. But the real action is happening in the overlapping hearts of the 2 spirals. Here, the compressed gas has ignited a firestorm of star formation, lighting up the collision zone with the brilliant blue light of countless newborn star clusters. These are not just individual stars, they are superstar clusters, dense groupings that can contain the mass of millions of suns, and may one day become globular clusters that will orbit the merged galaxy for billions of years to come. The entire region is a chaotic and beautiful stellar nursery, a testament to how destruction on a galactic scale can be the direct cause of the most profound acts of creation. The legacy of a starburst, however, is a double-edged sword. While it creates a spectacular display of brilliant young blue stars, it also exhausts the galaxy's future. By consuming its gas reservoir so rapidly, the starburst effectively guarantees that the galaxy will have a relatively short-lived period of brilliance followed by a very long, quiet retirement. Once the gas is gone, star formation ceases. The massive, hot blue stars born in the frenzy live fast and die young, exploding as supernova within a few million years. What remains is a galaxy increasingly dominated by the longer-lived, cooler, redder stars. The starburst, for all its fiery glory, is a galaxy's way of living its entire creative life in a magnificent, unsustainable, and breathtakingly beautiful flash. But if the aftermath of a galactic collision can forge new stars and reshape entire structures, it can also perform an even more incredible trick, building entirely new galaxies from the wreckage. We've been taught that galaxies form from the top down, coalescing within massive halos of dark matter that act as gravitational anchors. But the universe loves a good exception, and one of the most fascinating is the tidal dwarf galaxy. These are not cosmic giants born from primordial gas. They are celestial underdogs, assembled from the discarded material flung out during the violent mergers of their massive parents. The process begins with the same galactic collisions we've discussed, but with a different outcome. When two large spiral galaxies swing past each other, their gravitational interaction doesn't just trigger star formation within them. It can also rip vast streams of gas, dust, and stars right out of their disks, hurling this material into intergalactic space. These are the magnificent tidal tails we see in systems like the antennae galaxies, great arcs of luminous matter that can stretch for hundreds of thousands of light years. It is within these ejected streams that the magic happens. Gravity continues to work on this orphaned material. Dense knots within the tidal tail begin to collapse under their own weight, pulling in more and more of the surrounding debris. If a knot gathers enough mass, it can ignite star formation and ultimately coalesce into a stable, self-gravitating system, a brand new galaxy. The truly insane and revolutionary aspect of these tidal dwarf galaxies is their composition. According to our models, the dark matter halos of the parent galaxies are like vast, fluffy clouds. During a collision, the visible matter, the stars and gas, can be pulled out and stretched into these long tails because it's concentrated in the galactic disks and interacts through friction and gravity. But the dark matter halo, being a gigantic, diffuse sphere, doesn't get pulled out in the same way. It largely remains as a background gravitational field. This means the material that forms the tidal tails, and consequently the new tidal dwarf galaxies, is almost purely the normal baryonic matter we can see: stars, gas, and dust. These galaxies should, in theory, contain very little to no dark matter. This makes them living laboratories and crucial tests for our theories. Finding a galaxy that lacks dark matter would have been considered impossible just a few decades ago, but tidal dwarfs are predicted to be exactly that. Their rotation and dynamics should be governed solely by the gravity of their visible contents. Studying them allows astronomers to isolate the effects of normal matter and study a galaxy's behavior in a pure state, untouched by the dominant but invisible hand of dark matter. They are a brilliant demonstration of the universe's resourcefulness, proving that new galactic life can not only emerge from destruction, but can also break the fundamental mold we thought was required for all galaxies. Yet for all the violence and drama we observe in distant galaxies, it would be a mistake to think our own Milky Way is a passive bystander in the cosmic play. We might think of our galactic home as a relatively quiet, stable spiral, but evidence is mounting that it too has an explosive and tumultuous past, a history written in the sky in a language of high-energy light. In 2010, astronomers analyzing data from NASA's Fermi Gamma-Ray Space Telescope made a startling discovery. They found two colossal, identical structures billowing out from the galactic center, extending for 25,000 light-years both north and south of the galactic plane. These are the Fermi bubbles, and they are a stunning testament to a cataclysm that rocked our galaxy millions of years ago. To grasp their scale, you have to imagine something that dwarfs every other structure in our galaxy. Each bubble is so immense that it stretches halfway from the central black hole to the very edge of the Milky Way's disk. If our eyes could see in gamma rays, the highest energy form of light, the night sky would be dominated by this spectral hourglass figure, a pair of vast orbs glowing with the aftermath of an unimaginable release of power. Their edges are remarkably sharp, suggesting they were formed in a single, rapid, and incredibly energetic event, a brief but violent outburst rather than a slow, steady wind. The origin of these bubbles is one of the most active debates in galactic astronomy, but the prime suspect sits right at the center of it all, our supermassive black hole, Sagittarius A star. While it's relatively quiet today, the presence of these structures suggests it was not always so dormant. The leading theory posits that several million years ago, Sagittarius A star experienced a period of intense activity, likely as it consumed a massive clump of gas or even an entire star. This feast would have generated a titanic release of energy, not in the form of directed jets, but as a near-simultaneous explosion out of both poles of the black hole's accretion disk. This bipolar outburst would have blasted outwards at tremendous speed, punching through the surrounding interstellar material and inflating these giant bubbles of ultra-hot gas like a cosmic balloon. An alternative theory suggests the bubbles might be the cumulative result of a different kind of frenzy, not from the black hole itself, but from a period of intense star formation near the galactic center. If a wave of massive stars were born and then died in supernova explosions around the same time, the combined force of their stellar winds and detonations could have collectively blown these massive structures. However, the sheer symmetry and clean edges of the bubbles point more strongly to a single, concentrated point of origin, making the black hole outburst the more compelling explanation. The Fermi bubbles are more than just a fascinating relic. They are a direct message from our galaxy's past, proving that even our seemingly peaceful cosmic neighborhood is capable of generating violence on a scale we can barely comprehend. They serve as a powerful reminder that galaxies are not static museums but dynamic, evolving entities, with central engines that can awaken from their slumber and reshape their entire structure in a geological instant. This hidden history, written in gamma rays, tells us that our own galactic home has a dramatic and explosive story to tell. Just when you think you've seen every possible configuration of stars and gas, the universe unveils a structure so geometrically perfect and bizarre it seems almost engineered. Among the most visually striking of these galactic anomalies are polar ring galaxies, a rare class of systems that look like a brilliant celestial hula hoop has been thrown around a more conventional galaxy. In these extraordinary objects, a vast ring of stars, gas, and dust orbits not within the plane of the main galactic disk, but perpendicular to it, circling over the galaxy's poles in a dizzying display of cosmic ballet. The classic example, and one of the most studied, is NGC 4650A. At first glance, it appears as two distinct galaxies superimposed at a right angle. The central component is a lenticular or elliptical galaxy, a smooth, featureless collection of older, redder stars, but encircling it precisely at the poles is a stunning, bright ring, younger and bluer, teeming with the gas and dust needed for active star formation. This ring isn't a small accessory. It can be larger than the host galaxy itself, a gigantic structure of borrowed material orbiting in a plane that defies the usual rules of galactic motion. The prevailing theory for how these breathtaking structures form is a story of gravitational theft on an epic scale. Astronomers believe a smaller, gas-rich galaxy ventured too close to a larger, more massive one. As the two galaxies underwent a close encounter, the immense tidal forces from the larger galaxy didn't just distort the smaller one, they completely ripped it apart. The stars and dark matter of the victim galaxy were likely scattered, but its precious cargo of cold gas and dust was captured. Because this interaction wasn't a direct head-on collision but more of a glancing, perpendicular blow, the captured material didn't settle into the plane of the main disk. Instead, it was funneled into a stable orbit that circles over the poles, a perpetual reminder of a past cosmic cannibalism. This unique configuration is far more than just a beautiful curiosity. It provides astronomers with a one-of-a-kind natural laboratory for tackling the universe's biggest mystery, dark matter. We know galaxies are embedded within enormous spherical halos of this invisible substance, but mapping the precise shape and density of these halos is incredibly difficult. A polar ring galaxy offers a three-dimensional solution. Here, you have two components moving in completely different planes. The main stars of the central galaxy orbit within one plane, while the stars and gas of the ring orbit at a 90-degree angle to it. By carefully measuring the orbital speeds of both the central galaxy and the ring material, astronomers can effectively map the gravitational pull of the dark matter halo in 3 dimensions. The ring acts as a probe, tracing the gravitational field in a direction that is normally invisible to us, providing crucial data that helps us understand the true shape and distribution of the dark matter that dictates the fate of all galaxies. Yet for all the violent chaos and beautiful oddities we find across the cosmos, there is one image, one single observation, that perhaps more than any other fundamentally rewired our understanding of the universe's sheer abundance. It wasn't a discovery made by peering at a brilliant quasar or a colliding galaxy, but by the courageous decision to stare into what was thought to be nothingness. In December of 1995, the astronomers operating the Hubble Space Telescope aimed its powerful lens at a patch of sky near the Big Dipper that was, by all previous accounts, utterly empty. For 10 consecutive days across 150 separate orbits, Hubble collected the faintest trickles of light, photons that had been traveling for billions of years. The chosen target was no larger than a grain of sand held at arm's length, a minuscule fraction of the entire sky. The expectation, even among the project's proponents, was modest. They hoped to see a handful of very distant, faint galaxies. What they got back instead was a revelation that forever changed our place in the cosmos. When the final image was processed, it revealed not a void but a spectacular tapestry of light. That tiny, insignificant point was filled with over 3,000 distinct galaxies. Each one of those faint smudges was an entire island universe, some so young and distant that we were seeing them as they appeared just a few 100 million years after the Big Bang. The Hubble Deep Field, as it came to be known, was a core sample of the universe, a narrow but incredibly deep drill hole into the fabric of spacetime itself. It provided the first clear, insane statistical proof that the cosmos is not just sparsely populated with galaxies, but is absolutely saturated with them. Astronomers quickly did the math. If such a tiny, random speck of sky contained 3,000 galaxies, then the entire observable universe must contain at least 100 billion. That number, which we now know was a significant undercount, was so staggering that it instantly transformed our perspective. The universe was not a mostly empty dark ocean with a few scattered galaxies. It was a bustling metropolis of light, and we had just seen our first city map. But the deep field significance goes far beyond just a big number. It gave us something far more valuable, a family album of the cosmos. Because light takes time to travel, the image was a look back in time. The faintest, reddest galaxies in the frame were the youngest snapshots of galactic infancy. This allowed astronomers for the first time to study the evolution of galaxies across billions of years within a single frame. We could see small, irregular protogalaxies merging to form larger structures. We could witness the rapid star formation in the early universe, and we could test our theories of cosmic evolution against actual observational data stretching back to the dawn of time. It was the ultimate reality check, confirming that the process of hierarchical growth of small things merging to form larger things was indeed the primary engine of galaxy formation. The Hubble Deep Field was more than a picture. It was a portal, a direct window into the deepest reaches of space and time that instantly cemented the idea that to understand the universe, we must first understand the story of its galaxies. But just when we think we understand the rules of this cosmic dance, the universe introduces a twist so profound it challenges our very notion of gravitational destiny. We've seen how galaxies merge through violent collisions and how smaller satellites are consumed over eons, spiraling inward due to a subtle but relentless force known as dynamical friction. Imagine a small galaxy orbiting a much larger one, like a moon around a planet. As it moves through the larger galaxy's extensive halo of dark matter and stars, it experiences a gravitational drag, a kind of cosmic resistance. This interaction slowly bleeds away its orbital energy, causing its path to decay in a slow, inevitable spiral toward the center. It's a fate that seems inescapable, a gravitational marriage that has played out countless times across the universe, building the giant galaxies we see today. However, there is a competing force at work on the grandest of scales, one that operates not with a pull but with a push. For the past several billion years, the expansion of the universe has been accelerating, driven by the mysterious influence of dark energy. This isn't just a gentle stretching, it's a powerful anti-gravitational force that is causing the very fabric of space itself to expand at an ever-increasing rate. On intergalactic scales, this expansion creates what astronomers call the Hubble flow, the overall motion of galaxies receding from one another as the space between them grows. This sets the stage for a celestial tug-of-war of almost philosophical depth. On one side, you have the relentless local pull of gravity trying to draw two galaxies together. On the other, you have the global repulsive force of dark energy trying to push everything apart. For galaxies that are very close together, like the Milky Way and the Large Magellanic Cloud, gravity is the undisputed champion. Their mutual attraction is so strong that the expansion of the universe is irrelevant on such a small scale. Their fate is sealed in a slow-motion merger. But for a galaxy that is farther out, orbiting at a much greater distance within the larger galaxy's gravitational influence, the outcome is no longer certain. The incredible idea is that dark energy could actually interrupt and reverse the infall of such a satellite. Picture a smaller galaxy that has begun its multi-billion-year spiral inward, slowly losing energy to dynamical friction. Before it can complete its journey and be consumed, the accelerating expansion of the universe might become the dominant force in its region of space. The growing void between it and its parent galaxy would act like a rising tide, effectively severing the gravitational connection. The inward spiral would halt. Then it would reverse. This galaxy would never complete its merger. Instead of being consumed, it would be cast adrift, its motion overtaken by the Hubble flow. It would transition from being a satellite in a decaying orbit to becoming an independent galaxy once again, slowly receding into the expanding darkness, forever separated from the partner it was once falling toward. It's a cosmic boomerang effect, not thrown by hand, but by the fundamental forces of the universe itself, a gravitational embrace broken by the expansion of space. This isn't just theoretical. As our universe continues to age and dark energy's influence grows, this fate may await many distant satellites, leaving the largest galaxies forever isolated, their growth stunted, their future mergers cancelled by the accelerating tide of nothingness. But for all the grand collisions, violent cores, and accelerating expansion that defines the cosmos, there is one location whose specific, quiet properties are perhaps the most insane of all, our own. We have spent our journey exploring the farthest reaches and most extreme phenomena, but it's time to turn our gaze back home and appreciate the cosmic address we call the Milky Way. We are not residents of a chaotic downtown or a desolate rural outpost. Our solar system resides in what you might call the ultimate galactic suburb, and the specific conditions of this neighborhood are the reason you are here to hear this story. To understand just how fortunate our location is, imagine the galaxy as a vast metropolis. The bustling, energy-packed downtown is the galactic center. Here, near the supermassive black hole Sagittarius A*, space is a chaotic jumble. Stars are packed together millions of times more densely than in our local space, leading to frequent gravitational disruptions. The air is thick with intense radiation from the active nucleus and countless supernovae, sterilizing any potentially habitable worlds. This is no place for life to take root. It's a perpetual cosmic fireworks display. On the opposite extreme, far out in the remote galactic halo, you find the countryside. Here, the stars are ancient and widely scattered. The solitude is profound, but this peace comes at a great cost. These outer regions are impoverished, lacking the heavy elements forged in the hearts of massive stars and scattered by their explosive deaths. Elements like iron, oxygen, silicon, and carbon, the very building blocks of planets and life itself, are incredibly scarce out here. A planet forming in this region would likely be a small, rocky world without the necessary ingredients for a rich chemistry, or a gas giant without any solid ground at all. Our solar system, however, occupies a privileged middle ground. We are situated in the Orion Cygnus arm, roughly 27,000 light-years from the chaotic center. This places us squarely within what astronomers call the galactic habitable zone. This isn't a rigidly defined ring, but rather a sweet spot in the galaxy where a confluence of factors creates a safe and fertile environment for life. The first factor is safety. We are far enough from the dense core to avoid its intense radiation and gravitational turmoil, yet we are not so far out that we are completely isolated from the galaxy's chemical wealth. This brings us to the second factor, enrichment. Our suburb has been seeded with just the right amount of heavy elements. We are close enough to previous generations of stars that their supernova explosions have fertilized our local interstellar medium with a rich mix of elements, but not so close that these same explosions would frequently scour our planetary system clean of life. It's a delicate balance. A supernova too close within about 30 light-years would be a catastrophic event, bathing our world in lethal radiation. Our location ensures that such events are rare, while still allowing our system to form from a cloud that was rich in the materials needed to build a robust terrestrial planet like Earth. Finally, our orbit itself provides a remarkable stability. The Sun's path around the galactic center is nearly circular, keeping us at a consistent distance from the dangers of the inner galaxy. It also keeps us synchronized with the galaxy's spiral pattern, allowing our system to pass between the dense spiral arms rather than being stuck inside one. Spiral arms are regions of compressed gas and active star formation, which also means they are hotspots for supernova. Our orbit ensures we spend most of our time in the quieter inter-arm regions, minimizing our exposure to potential stellar cataclysms. This perfect positioning is an insane bit of cosmic real estate luck. It provided a stable platform for our solar system to form 4.6 billion years ago with all the necessary ingredients, and it has offered a quiet, safe harbor for life to evolve over billions of years without being wiped out by a galactic disaster. Out of the hundreds of billions of stars in our galaxy, only a fraction occupy this privileged zone. Our existence is tied to this specific, fortunate location, a gentle world in a quiet neighborhood orbiting a stable star in the peaceful suburbs of a majestic spiral galaxy. But while we often marvel at the shapes and motions of galaxies, there's a hidden chemical story written into every single star, a narrative of cosmic recycling that defines the very substance of planets and life itself. In the language of astronomy, the term metal carries a meaning far different from its use here on Earth. To an astronomer, any element heavier than the two primordial giants, hydrogen and helium, is classified as a metal. This includes the oxygen we breathe, the carbon that forms our bones, the silicon in rocks, and the iron at the core of our planet. This expansive definition exists for one simple reason. In the grand scheme of the universe, these heavier elements are incredibly rare, the precious and scattered ashes of stellar furnaces long since extinguished. The very first galaxies to ignite in the early cosmos were pristine environments, composed almost entirely of hydrogen and helium left over from the Big Bang. They were vast, simple, and chemically pure, but also barren, incapable of forming rocky planets or the complex chemistry required for life. The transformation of these galaxies from simple to complex is the story of metallicity, the measure of the fraction of a galaxy's mass that is made up of these heavier elements. A galaxy's metallicity is its chemical fingerprint, a direct record of its star-forming history and its age. This process of cosmic enrichment is driven entirely by the life and death of stars. Inside the cores of stars, nuclear fusion doesn't just create light and heat. It acts as a colossal forge, hammering lighter elements into heavier ones. A star like our Sun fuses hydrogen into helium, but more massive stars burning hotter and under greater pressure can take this process much further, creating carbon, oxygen, neon, and all the way up to iron in their layered interiors. However, this forging only goes so far. The final act of creation requires a stellar death. When a massive star exhausts its fuel, its core collapses and then rebounds in a cataclysmic supernova explosion. The incredible energy of this detonation is enough to fuse elements heavier than iron, like gold, silver, and uranium. More importantly, the explosion blasts the star's newly forged elements, and the ones created in the supernova itself, out into the surrounding interstellar gas, seeding it with the raw materials for new stars and planets. This means that every star carries a chemical timestamp. A star formed from that primordial hydrogen and helium gas will have extremely low metallicity. It is a first-generation star, a relic from the universe's youth. When that star dies and enriches the surrounding cloud, the next generation of stars born from that cloud will inherit those heavier elements, boasting a higher metallicity. Our own Sun is a stellar third-generation citizen. It contains a rich mixture of these heavier elements, which means it was born from a cloud of gas that had already been seeded by two previous generations of stars that lived, died, and scattered their enriched guts across the galaxy. The very planets that orbit it, including our Earth, are literally made from the debris of those long-dead stars. Every atom of oxygen in water, every bit of calcium in our bones, every piece of iron in our blood was once part of a star that ended its life in a spectacular explosion billions of years ago. By measuring the metallicity of stars across a galaxy, astronomers can read this layered history like a book, identifying the oldest stellar populations and tracing the gradual process of enrichment that made our own existence not just possible but inevitable. And yet, despite all the brilliant chaos, the violent mergers, and the intricate cosmic web that connects everything, this grand and dynamic universe has an expiration date. We've explored how galaxies live and die, but we must now confront the ultimate, and perhaps most profoundly lonely, fate that awaits them all. The story of our universe isn't one of endless cycles. It's a narrative with a final, silent chapter written by a mysterious force we've only just begun to comprehend: dark energy. For the last several billion years, the expansion of the universe hasn't just been continuing, it's been accelerating. Think of it not as a ball rolling gently down a hill, but as a car pressing harder and harder on the gas pedal with every passing moment. This acceleration is driven by dark energy, a repulsive force that seems to be an inherent property of the fabric of space itself. Right now, its effects are subtle on the scale of our local group of galaxies where gravity still holds supreme. The Milky Way's gravitational bond with Andromeda is so strong that they are destined to merge, and the smaller galaxies orbiting us are still safely held in our grasp. But on the largest scales beyond our local gravitational island, dark energy is the undisputed ruler. Now, let's project this accelerating expansion trillions of years into the future. The consequences are not just dramatic, they are absolute. Every single galaxy that is not gravitationally bound to us, which is every galaxy outside our local group, is moving away from us faster and faster. As space itself stretches at an ever-increasing rate, the distance between our galactic island and all others grows at a speed that will eventually surpass the speed of light. This doesn't violate the rule that nothing can travel through space faster than light. It's the space between us that is expanding, carrying the galaxies away like raisins in a rapidly inflating loaf of bread. The insane result of this is that the light from those distant galaxies desperately trying to reach us will be fighting a losing battle against the stretching of space. The wavelengths of their photons will be stretched into oblivion, shifting far beyond the infrared into wavelengths so long they are undetectable. Their light will effectively be lost, its energy drained away by the expansion. One by one, and then in a final collective fade, every galaxy beyond our local group will redshift directly out of our observable universe. They won't have moved to a different location. The space between us will have expanded so much that they are forever beyond any possible causal contact. Now picture an astronomer living in that far future, on a world orbiting a star in the merged galaxy of Andromeda. They will peer out into the cosmos with technology far more advanced than ours, and they will see nothing. An endless, static black void. The thousands of galaxies we see today in our deep field images, the magnificent cosmic web, the brilliant quasars, all of it will be gone from view. Their entire observable universe will consist of their own galaxy and its few nearby bound companions. All evidence of the expanding universe, the redshift, and even the Big Bang itself will have vanished over the cosmological horizon. The cosmic microwave background radiation, the afterglow of creation, will have been stretched to wavelengths longer than the diameter of the known universe, rendering it completely undetectable. This future civilization will be living in an island universe in the most literal sense, trapped in a cosmic isolation of unimaginable scale. With no external points of reference, they would have no way of knowing the universe was ever expanding or that it began in a hot, dense state. Their cosmology would be built on a fundamentally incomplete picture, forever blind to the true nature of reality. It's a hauntingly lonely thought that the universe itself will eventually hide its own history, leaving any future beings with a silent, empty sky, forever unaware of the breathtakingly vast and vibrant cosmos that once was. And so we reach the end of our journey through 30 of the universe's most incredible secrets, and if there's one overarching truth to take away, it's this: a galaxy is so much more than a simple island of stars. It is a dynamic, violent, and ceaselessly creative engine of cosmic evolution. We've seen how they are born in the aftermath of the Big Bang, how they grow by consuming their neighbors, how they are shaped by invisible dark matter and regulated by the violent hearts of supermassive black holes. They are not static paintings, they are living, breathing entities with life cycles, from the fiery starbursts of their youth to the quiet, red retirement of their old age. Every single fact we've explored peels back a layer of the cosmic onion, revealing a universe that is far more complex, more bizarre, and more wonderfully strange than we could have ever imagined just a century ago. And with every layer we remove, with every mystery we solve, like the flat rotation curve or the nature of quasars, we are confronted by two even deeper, more fundamental puzzles: dark matter and dark energy. These are the twin pillars of modern cosmology, the great unknowns that constitute 95% of the universe yet remain completely invisible to our telescopes. They are the ultimate reminder that our exploration has just begun, and that the greatest discoveries about the nature of reality itself are still waiting for us out there in the dark. The next time you find yourself under a clear night sky, I hope you see it differently. I hope you look up and not only see the serene beauty of the stars, but also feel the incredible dynamic chaos they represent. See the grand dance of Milky Way and Andromeda, locked in their multi-billion-year embrace. Sense the invisible halo of dark matter that holds our galaxy together, and feel the faint, ghostly pull of the great attractor drawing our entire supercluster toward an unseen destiny. You are a living part of this grand story, a conscious witness to a cosmos of boundless wonder. Now, we'd love to hear from you. Which of these 30 facts completely rewired your brain? Was it the galactic cannibalism happening right now in our own Milky Way, the ghostly galaxy made almost entirely of dark matter? Or the mind-bending reality that our entire solar system has completed only 20 orbits around the galaxy? Let us know in the comments below which insight struck you the most. If this journey into the cosmic deep has left you hungry for more, be sure to subscribe and hit the notification bell so you don't miss our next adventure into the secrets of the universe. The cosmos is full of mysteries, and we're just getting started. Thank you for watching.